Hello students, welcome to MGC Learning. I am Manju Dilip. Today I am going to start with the 12th standard mathematics topic, applications of derivatives part 2. We already studied in the previous video about equation of tangent, equation of normal, etc. Now today we are starting with the topic derivative as rate measure and we are solving some questions in this topic. So we'll start with the derivative of this one. So y is equal to f of x is a function. Then the change in x from x1 to x2 is generally denoted by delta x is equal to x2 minus x1. So corresponding change in y is delta y is equal to f of x2 minus f of x1. Then the ratio delta y upon delta x is equal to f of x2 minus f of x1 upon x2 minus x1 is called average rate of change with respect to x. If we are applying limit to both sides of this equation will become f dash x1, that is the slope of the tangent to the curve y is equal to f of x at p of x1 comma f of x1 is called the instantaneous rate of change of y with respect to x at x is equal to x1. So when we are applying limit to this function, left hand side will become dy upon dx. This is the definition of derivative. Limit delta x tends to 0, delta y upon delta x we already studied in previous chapter. That is dy upon dx is equal to, or f of f dash x1 is equal to limit x2 tends to x1 f of x2 minus f of x1 upon x2 minus x1. This is also called slope of the tangent also. And when we are applying x is equal to a, this will become slope of the tangent to y is equal to f of x at a f of a, that point. We'll start with question. A spherical soap bubble is expanding so that its radius is increasing at the rate of 0.02 centimeter per second. At what rate is the surface area is increasing when its radius is 5 centimeter? So while reading the question, which are the terms given in this question you have to remember so that you can give the proper alphabet to that as the assumption. So spherical spoke bubble is given. It is expanding. That means its radius is increasing at the rate is given. That is dr upon dt is given. That is 0.02 centimeter per second. Now radius is 5 centimeter is also given in the question, and you have to find out what a rate is the surface area is increasing. Surface area, if you are considering capital A for surface area, then dA upon dt you have to find out. So let r be the radius and a be the surface area of this spherical soap bubble at time t seconds. Then we have to consider a is equal to 4 pi r square. 4 pi r square is the surface area of a sphere. Now you have to find what rate the surface area is increasing. That means dA upon dt you have to find out. So you have to take derivative of this function with respect to t. So dA upon dt is equal to 4 pi into 2r into dr upon dt. Now in this question it is given as dr upon dt is equal to 0.02 and r value is 5 centimeter. So you can substitute these values in equation number 1. So 8 pi into 5 into 0.02, that's equal to 0.8 into 22 upon 7. This pi value is 22 upon 7 I am giving, is equal to 2.514. So the surface area of a soap bubble is increasing at the rate of 2.514 centimeter square per second is the answer for this question. Next question is, the surface area of a spherical balloon is increasing at the rate of 2 centimeter square per second. At what rate the volume of the balloon is increasing when radius of the balloon is 6 centimeter? So let R be the radius, capital A be the surface area and V be the volume of the spherical balloon at time t seconds, because surface area is mentioning, that is capital letter A, and rate of volume they are asking, what rate they are asking, that means dV upon d2 we have to find out, and radius is also given. So we have to assume like that. Spherical balloon's surface area is increasing is given, so A you have to consider as 4 pi r square. So dA upon dt is given So that you have to find that also. So dA upon dt is equal to 4 pi into 2r dr upon dt, that's equal to 8 pi r into dr upon dt. This is equation number 1. And it is already given as dA upon dt is 2 centimeter square per second. So we'll consider that also. Since equation number 1 and 2 are same in left hand side, right hand side we can equate. So equating 2 is equal to 8 by r into dr upon dt. Cancelling, you will get the r into dr upon dt is equal to 1 upon 4 pi. That is equation number 3. Now we have to find the volume and rate of change of volume of this balloon we have to find out. For that we have to consider volume of a sphere. V is equal to 4 by 3 pi r cube. So derivative we have to find out, is clear. Derivative of v with respect to t is dv upon dt is equal to 4 upon 3 pi into 3r square dr upon dt. Given r is equal to 6 centimeter in this question, dv upon dt is equal to 4 upon 3 pi into, you have to substitute this value so that you can find the value. So I am splitting this r into r square into 3r into r dr upon dt, so that I can substitute r dr upon dt by using equation number 3. So dv upon dt is equal to 4, 3 cancel, 4 pi r into, for this value 1 upon 4 pi. So 4 pi cancel, that's equal to r, that's equal to 6 centimeter cube per second is the rate of change of volume of this balloon, spherical balloon. This is the answer for this question. Next question is, if each side of an equilateral triangle increases at the rate of root 2 centimeter per second, find the rate of increase of its area when its side of length 3 centimeter. So each side of an equilateral triangle increases. That means side is increasing. So we have to consider small letter a for the side. So dA upon dt is given as root 2 centimeter per second. Now the length, each side length is given as a is equal to 3 centimeter, and you have to find out what rate its area is increasing. So d capital A upon dt you have to find out. So let A be the side and capital A be the area of the equilateral triangle at time t seconds. So we have to find rate of change of area. For that we have to consider this. So A is equal to root 3 upon 4. A square is the area of equilateral triangle. Taking derivative, dA upon dt is equal to root 3 upon 4 into 2a into dA upon dt. We have to substitute these values. It is given as a is equal to 3 centimeter, dA upon dt is equal to root 2 centimeter per second. So we can substitute these values in this one. So dA upon dt is equal to root 3 upon 2 into, in the place of a it is 3 and dA upon dt is root 2. So root 3 into root 2 is root 6. So 3 root 6 upon 2 centimeter square per second. Therefore, the rate of increase of the area of the equilateral triangle is 3 root 6 upon 2 centimeter square per second is the answer for this question. Next question is, the edge of a cube is decreasing at the rate of 0.6 centimeter per second. Find the rate at which its volume is decreasing when the edge of the cube is 2 centimeter. So edge of a cube is given. So we can consider that is small letter a, that is 0.6 centimeter. 2 centimeter, and it is given the edge of a cube is decreasing. So it is either it is increasing or decreasing. So rate of change of increasing or decreasing we will consider as derivative. So dA upon dt is given as 0.6 centimeter per second. Find the rate at which its volume is decreasing when the edge of the cube is 2 centimeters given. So volume dv upon dt you have to find out here. So let a be the edge and v be the volume of the cube at time t seconds. We have to find dv upon dt. For that we are considering v is equal to a cube. This is the volume of a cube. So taking derivative, dv upon dt is equal to 3a square into dA upon dt. So dA upon dt is equal to 0.6 centimeter per second is given, and side A is equal to 2 centimeter is given. We will substitute these values in this equation. Number 1, dA upon dt is equal to 3 into 2 square into 0.6, that is 7.2 centimeter cube per second is the answer. So rate at which the volume of the cube is increasing is 7.2 centimeter cube per second. Next question. A ladder 10 meter long is leaning against a vertical wall. If the bottom of the ladder is pulled horizontally away from the wall at the rate of 1.2 meters per second, Find how fast the top of the ladder is sliding down the wall when the bottom is 6 meters away from the wall is given. So one ladder of length 10 meter we have to consider. So for that we have to draw a rough diagram. So AB be the ladder and the length of this ladder is 10 meter is given. If the bottom of the ladder is pulled horizontally, that means this is the bottom B. So this bottom is pulled away from the wall or vertical wall. This is vertical wall OA and OB is the distance of the bottom of the ladder to the wall. So this is increasing. Find how fast the top of the ladder is sliding. This how fast this is sliding towards the down towards the bottom is 6 meters away from the wall. This is 6 meters away from the wall is given. Then AB be the ladder and OA is equal to Y and OB is equal to X. We have to assume it is given as dx upon dt. That means this is the bottom of the ladder is moving away from the wall at the rate of 1.2 meter per second. So dx upon dt is 1.2 meter per second. From the figure we get x square plus y square is equal to 10 square because we don't know the value of x and y here. So by using Pythagoras theorem, you can apply x square plus y square is equal to 10 square. Differentiating with respect to t, 2x dx upon dt plus 2y dy upon dt is equal to 0. Now dx upon dt is given. So we can substitute that value. So before that I have to adjust this one. So dy upon dt is equal to minus x dx upon y dt. Now only x value we know that, so we don't have this y value, but we can find this value from this one. X value is given as 6 centimeter. So substituting that value in this equation number 1, we will get y value. So 6 square plus y square is equal to 10 square. Now y square is equal to 64, therefore y is equal to 8. From 2, we can substitute this value dy upon dt is equal to minus, in the place of x it is 6, dx upon dt is 1.2 upon y value is 8. So substituting you are getting minus 0.9. Therefore, the top of the ladder is sliding down at the rate of 0.9 meter per second. We are not considering negative because this is decreasing value. That is why minus symbol is there. So this is the final answer for this question. Next topic is velocity, acceleration and jerk. If S is equal to f of t is the displacement of a particle, then f dash t, first derivative of this is called velocity. The rate of change of displacement s with respect to time is velocity. So f dash t is the velocity of the particle. The speed of the particle is the absolute value of the velocity, that is modulus of f dash t. The rate of change of velocity with respect to time is called acceleration and it is denoted by a of t. So a of t is equal to derivative of first derivative of velocity, that is v dash t, and second derivative, 2 times if you are taking derivative of displacement you will get acceleration. Now, if you are considering third derivative of the function as a displacement s triple dash t is equal to 2 times derivative of second derivative of velocity is equal to 1 first derivative of acceleration is called the jerk. So, if you are taking 3 times derivative of displacement, you are getting jerk, or 2 times derivative of velocity is jerk, or 1 time derivative of acceleration is jerk. Jerk J is the rate of change of acceleration. So rate of change of displacement is velocity. Rate of change of velocity is acceleration. Rate of change of acceleration is jerk. Now some exercise questions are given to you. You have to solve it. Thank you.